My name is Meng Lu. I'm from Daimler, the Netherlands. I'm the program chair of IEEE IV this year. And it's my privilege this morning to introduce our keynote speaker, Dariu Gavrila. And he's a part-time professor of University of Amsterdam, and currently he's working for Daimler research in Ulm. He received his PhD in computer science from University of Maryland. And today he will tell us his view about smart cars for safe pedestrians. The floor is yours.
Thank you very much. Can you hear me? Well, good morning, everybody, and thank you for the introduction. It's a great pleasure to be here at the Intelligent Vehicles Conference to talk about the theme that I've been excited about for the past decade or so, smart cars for safe pedestrians. It's a very rewarding theme. It's a theme that has seen considerable progress over the past time period, and I'd like to go over some of the factors that have contributed to the success and also touch upon some of the ongoing research issues. Now, when people originally thought about intelligent machines, they probably had something like this in mind. Okay, so here is Robbie the robot, a rather clunky creature that would help us with all kind of tedious chores in the household, like fetching the phone and washing the dishes, cleaning up. And so that was kind of nice, but after a while, this view of Robbie evolved in something more human-like in terms of appearance, but also in terms of personality. And so we get to this picture, which is also still a butler, but is also self-aware and has some own personality. Although some people seem to have a different, more menacing view of future machine intelligence. But why wait for the future? Because the future is already here in terms the first large-scale deployment of embodied machine intelligence is already with us, and it comes in a form that's very familiar to us. It's our modern car. Modern cars have sensors to survey the surroundings. They extract information. They reason upon this information, and they act upon the environment. So that's the classical embedded AI system. And machine intelligence comes to us in bits and pieces that we call driver assistance functions. They help us operate the vehicle in more safe, comfortable, and energy-efficient fashion. And you can see here a whole bunch of driver assistance functions that are currently available on the market. And we see the driver assistance as a stepping stone to fully autonomous driving, on which we had a really nice keynote talk yesterday. And by focusing, though, on this intermediate step where the driver is still involved, and by focusing on cheap and reliable hardware, we can make an impact on traffic safety now and with every new vehicle generation that we introduce onto the market. Okay, so let's assume that we are driving downtown and the kids in the back are making a fuss, or we're just about turning the radio or the typing in our destination at the navigation unit. When we're not paying attention, when suddenly a child runs onto the street just in front of the vehicle. And this is a very typical dangerous situation that can happen, in particular if the driver is not paying attention or visibility conditions are poor, perhaps at night. And the plight of the so-called vulnerable road users, pedestrians and bicyclists, has always had a very strong emotional appeal, because of pictures like this. But it's not just emotions, it's also hard figures. If you take a look at the traffic fatalities under pedestrians and bicyclists, and I'm borrowing here from a nice illustration from our colleagues from Bosch, you can see that if you take a look at the EU, you can see that a quarter of all traffic fatalities involve pedestrians and bicyclists. And that comes down to about 8 to 10,000 traffic deaths, depending on how many countries you count or which year you take. Now, in some countries, this rate is lower, like in the US, it's only 13%. I take it that nobody is walking there, everybody's driving, right? Although in some other countries, like Japan and Korea, you can see that the percentage is in excess of 40%. So that's very significant. If you would like to see, where are the total numbers coming from, the total accident numbers in the world, then you have to consider the large developing economies like India, like China, and that's where a lot of these numbers add up, and the large numbers are. And there are two trends. On one hand, you have that these countries improve their traffic infrastructure, they improve the vehicles on the road. On the other hand, you have increased motorization, and these two effects tend to cancel out for the foreseeable future. That means that this topic of vulnerable road users is going to remain important for the next time to come. Now, triggered by these accident numbers, there has been a lot of initiatives also from the legislative part. The EU has been very active on pedestrian safety, and on top of that, there are consumer rating agencies like Euro NCAP, and that wield a considerable influence on this topic, because they can award or they can take away a maximum star rating based on whether a particular car passes or fails particular pedestrian safety tests. And up to now, Euro NCAP has only considered passive pedestrian safety. But starting 2014, there is the plan to also include active pedestrian safety. So the use of sensor systems and the use of active vehicle control. So that's going to be really interesting. So what we want to do in this whole theme is to develop systems that use sensors to detect dangerous situations with pedestrians and bicyclists in order to either warn the driver or to take control of the vehicle. And the primary sensing technology is video. That's because video has a large resolution, vertically and horizontally, and so it allows you to get a good object discrimination against the background. But still, the problem is very tough, and that's why we have been working for a decade on it. And it's very tough because of the large variation in pedestrian appearance, induced by viewpoint, induced by clothing, by the pose. And we have dynamic and cluttered backgrounds, and pedestrian exhibits rather irregular motion, or can exhibit irregular motion, which makes it hard for path prediction or a situation assessment module to figure out what's going on. And of course, we need to process in real time, and we have very high performance requirements, especially if we're thinking of applying emergency measures. So that's pretty much this package is pretty much the worst of computer vision and intelligent vehicle systems, but that makes it also very challenging. And the methods that are involved is a very interesting cross-section of computer vision and sensor processing, which makes this topic very attractive also from scientific point of view. Okay, now I love this historical perspective, and I excavated some pictures from our first major pedestrian demo in front of the Daimler Chrysler Board of Directors in '99. Here you see some of my colleagues and myself, a little bit younger, and we were in an indoor setting. So we were walking around, and there was some carpet, some painted carpet here, and there was some traffic signs, and the system, it was able to transform this rather sterile scene into this virtual world here, where these icons would be kind of floating around as we would be moving here. Well, this system used a bunch of PCs, and I recall we tucked them away under the table behind a black cloth because we didn't want our directors to see that this would never fit in a trunk, right? And another thing was that the sensing was rather fragile. I'm not sure what would have happened if we would have placed here a chair. Probably a new pedestrian would have shown up. But now, today, the field is rather mature. And there are many universities, there are most suppliers, and pretty much all OEMs are working on pedestrian safety. And first products have already reached the market. And you can basically distinguish three main application settings. We have the scenario for the far range for secondary roads. Typically at nighttime, you have the intermediate range for the urban environment, the classical pre-crash scenario. And you have the setting for the immediate neighborhood of the vehicle, the surround view, and that's to help the driver maneuver his vehicle. So when you're parking out or you're turning around, then you would like to see what pedestrians or bicyclists are around you. And, well, you can imagine that these settings have quite a diverse set of requirements in terms of the vehicle speed involved, in terms of the sensor range and field of view, and also in terms of the performance that is necessary, because you can imagine that an application which provides information or warning is more forgiving than one which does emergency braking. And, well, I'm going to focus on this scenario here because that's the scenario where most benefit is to be expected in terms of the accident numbers. But I should say that most techniques and most concepts I talk about equally apply to the others. Okay. So we started after our demo. It took us 4 more years to have the first large-scale tests in the urban environment in 2003. And this was in the city of Aachen in Germany. And we had a terrible performance because we got only 40% of the pedestrians outside on the road. And we had an amazing 600 false trajectories per hour, which is about 10 per minute. So this system was hallucinating like 10 pedestrians per minute out of nowhere, right? So, but then 2 years later, we were reducing the false positives by an order of magnitude nearly, and nobody was honking anymore because now we were driving 40, and we increased the detection rate. And then again, 3 years later, another order of magnitude, significant improvement in detection rate. And now we are over here, so that really brings it into an area where you can have some very convincing applications. Now, this is the Daimler progress, but it's also indicative of some of the larger progress that has been made in the community in this area. So the question then is, what made this progress possible? Well, the first thing that brought us forward was, of course, better algorithms. And the architecture for such pedestrian system converged after a while in the community to something like shown over here. We have a set of modules. We start out with a region of interest generation module, which could use stereo or optical flow if we have only monocular vision. Or we can use geometry cues. We can assume that pedestrians walk on the ground plane and we have a flat ground plane. And so you get a bunch of windows which are then tested by this classification module. And for those that pass, we integrate them temporally, and you perform tracking. And at this point is the point where you would fuse with any other sensors that you might have, for example, radar. And then you're off to path prediction and driver warning and vehicle control. Okay, so that seems rather a logical architecture. I had lengthy discussions over time with some of my colleagues about the need for this separate pedestrian classification module, because the thinking was, well, if we're doing stereo-based obstacle detection here, perhaps we can sidestep this module and go straight to tracking and the rest. Well, I've always argued for the separate module on pedestrian classification because it brings some major advantages. The main advantage by having this module over here is that you, in essence, have two modules that do obstacle detection, that detect pedestrians. Okay, you have this module, which, well, obstacle detection using stereo means that you have a bottom-up approach, a data-driven approach, and classification means that you have a top-down approach matching with trained samples. And these algorithms are very complementary, and by combining them in a cascade, you can massively reduce false positives, and then you can get the performances that are required for these emergency types of maneuvering. And then certainly, once you know what object you're dealing with, you can devise specific driver assistance function. So if you say, okay, I've confirmed a pedestrian, then I could brake earlier or brake harder. So you can apply some object-specific reasoning there. And one thing that I think that we ought to do more on is to take advantage of the knowledge that we have about the kinematics of the object class and take advantage of the typical motion patterns that we see in order to do better path prediction and to arrive to better situation analysis. Okay, so now I've convinced you for the need for a separate pedestrian classification module, and I'd like to focus in on some of the work that has happened in this area. I think that the first milestone was that we derived good image features and good pattern classifiers for the pedestrian application, and I'd like to highlight work that I thought was very influential, the work by Viola and Jones for the R-wave Litsunada boost cascade, because that allowed for the first time to have an intensity classifier that you could slide over the full image in real time. Then you have the work by Dalla and Triggs on the Hawk features and linear support vector machines, where the Hawk features are highly optimized features and work very well. And then there's some work coming from the neural net community on convolutional networks. And convolutional networks means that the nodes from the hidden layer have only a local receptive field, so they're only locally, which saves us a lot of these weights compared to full connectivity. Okay. And there have been a lot of people that have contributed then to the pedestrian detection application in itself, people from the computer vision community, but also people from the IV community, people like Brogy, Fernandez Yorca, Sotelo, Kalhammer, Nadevsky, and Shashua, just to name a few. Okay, now the second milestone, I think, was the realization that by combining complementary image features and fusing the output of the classifiers, we could get much better performance. And so in some work that Markus Ensweiler and I did, and we published last year on transaction on processing, on image processing, what we do is we combine these Hawk features, which are an essential edge or gradient features. We combine them with local binary patterns, which encode texture or region features, okay? So these are complementary, and furthermore, we not only consider the typical intensity images, but also dense stereo images and dense optical flow images, okay? And in addition, as a third criteria, we have that we distinguish by the pose of the pedestrian by the viewpoint. So now what we do is we have three criteria, and for each combination of these criteria, we train separate classifiers, classifiers that are expert for this particular combination. And the overall result is a weighing of the individual classifiers, and the technical term is mixture of experts. Now, if you take a look at the performance, you can see that when we're comparing against the plain vanilla Hawk, the Dalla and Triggs Hawk, then you can see that by doing all this stuff, that we get an amazing 42-factor improvement in terms of reducing the false positive rate at equal detection rate. Okay, so, and another thing that brought us forward was the use of dense stereo. Dense stereo is good for accurate region of interest generation. Dense stereo helps for the classification of pedestrians. We showed that by taking intensity images and dense stereo images, we get an improvement of factor 4. And this is why I wanted to show you this video clip, it is very good at localization of the pedestrian. There's no sound here, but. So this is the 3D map, color-coded, and now we're going to have fly in the 3D world. And you can see how accurate, I believe, this 3D data is. Okay. Now, the second point of advantage was better hardware. We are hitching a ride on Moore's law, and in fact, we're doing even better than Moore's law because we're porting our algorithms to embedded hardware like FPGAs and DSPs. And so then we get even a steeper performance curve. And the reason we do that is because of power consumption. If you take a look at the Intel chip, Core i7, it takes about 100 watts, whereas Exciting Spartan only takes 5 watts. And so we have ported successively our components, like shape-based object detection in 2002, and more recently, the dense stereo computation. Having market-grade stereo, we believe is enabling technology for intelligent vehicles applications. And my colleague, Uwe Franke, has been very passionate about this and has pushed this forward within Daimler. And then as a last point here, we have pedestrian classification on FPGA. Now, the third point that brought us forward was more data. Okay, we early on figured out that, okay, it's clear that if you train on more data, you're going to do better. Okay, that's not a big deal. So here we have some experiments where we're doubling the number of pedestrians samples in a training data set. And we're looking again at the ROC, meaning here we have the detection rate versus the false positive rate. This is the ideal point, that we detect all the pedestrians and no false positives. So each time that we're doubling the trainings set for the pedestrians, you see that performance improves by the same factor because you reduce the false positive rate. Now, we have much larger data sets now, so this relation is not linear anymore, but still it points very early on the advantage of having a large data set. Of course, the labeling of pedestrians in images is very time-consuming and rather tedious, so a lot of our effort goes into devising intelligent tools and techniques to acquire and enrich the data that we collect. And we have, meanwhile, well, we started out in Ulm. That's the center where we started with the pedestrian detection. So we pretty much recorded all pedestrians in Ulm. But then we extended to Stuttgart, Munich, and some other cities over here. And meanwhile, we have in the order of tens of millions of images with pedestrians. And we have in the order of millions of labels. We also wanted to see if we can take a shortcut and to avoid this very tedious labeling, especially the students requested this. And so we did some work also with students on ways of generating artificial training data. And I'm not going to go into the details, but the main point is that we have a generative model that describes pedestrian appearance, and it consists from 3 components: the shape of the pedestrian, the texture within the pedestrian, and the texture in the immediate neighborhood of the pedestrian. And well, we transform the image-based representation into a model-space representation, which is a low-dimensional representation, We fit a probabilistic model on it. Could be like mixture of experts or Parson windows. And then we synthesize these components. That means that we get a synthesized shape, texture of the foreground, and texture of the background. And then we put it all together, and we get a synthesized, a virtual pedestrian. And you can see here some of the variations that we can obtain. Here we just vary the shape. So this guy is getting thicker by the second. But you can also see the typical pose, the gait phase being varied. We exaggerated a little bit this part just to see it better in the audience, but this is basically the idea. And in terms of texture, you can see here some of the effects that you get if you just vary that component. My favorite is this guy over here, because we have several appearance models for frontal, sideway, and backward views. And you can see for the frontal view that you get this very specific pattern that's only in the frontal view of the shirt and the coat. Okay, and so we would add these samples to our existing data set and improve such a way the performance of the classification. The last piece of the puzzle of performance is, in my opinion, extensive evaluation. A number of institutions have contributed over the years a number of data sets and a number of benchmark studies. And so have we at Daimler, and these data sets are publicly available. You can download them. You can do a web search to retrieve them. And we started out in 2006 with a data set on pedestrian classification, meaning that we have cutouts of pedestrians, of non-pedestrians. And then later on, we extended this data set to also include dense stereo and dense optical flow. So that's the data set that we use, that the mixture of experts study. And furthermore, we also included partially occluded pedestrians in the data set. And that's this data set over here. And then we have our data sets, our benchmarks on pedestrian detection, meaning that here we have labeled pedestrians in images and we have sequences. So here is a test set of driving through the city of Aachen for half an hour, and all pedestrians are painstakingly labeled. Okay, so this gives you about, I think about 50,000 pedestrian labels corresponding to 259 different pedestrians. So I think benchmarking is really important to obtain a visibility where to allocate research resources. And I think that that's something that we ought to do more in the IV community. And I was very glad to have noticed that also our colleague Christoph Stiller at the Karlsruhe Institute of Technology recently contributed a benchmark data set on stereo, optical flow, and image-based localization tracking. And so I think that that's really the way to go forward. Once we have tested things on the sensing component, we can go and test things at the overall system level. And I find it useful to distinguish whether we use real or fake pedestrians and vehicles. Okay? So in the quadrant of real pedestrians and real vehicles, well, these are the typical tests that we would do on the urban environment. And that really works well for the sensor component because that's a realistic setting. But it's a bit harder to test the full system because evidently you can only test the false alarms. You wouldn't want to test how well the system is working in real, in real dangerous situations, if that would mean that you would have to provoke these situations. So for that, you would take that system and you keep the parameters fixed, and you go to the test track where you could test your system up to collision by using a pedestrian dummy. But of course, this pedestrian dummy doesn't really look human, right? I mean, it can't walk, and if you use several sensors, maybe you use radar and you use infrared, it's hard to get dummies that are very realistic in terms of all the sensor types that you might be using. So we did some work in some EU project on performing pre-crash tests with real pedestrians and do that safely. And I will show you some videos later on this. And the last quadrant is simulation. This has the big benefit that you could exhaustively scan through a number of critical scenarios and vary several parameters, and you can test your system. Up to now, the realism of the rendered scenes were maybe not that impressive, but with progress in graphics and better game engines, I think that it will soon be an integral part of any future pedestrian testing simulation. Okay, so let's look at the test track and some of the tests we did 2-3 years ago on automatic braking versus evasion. So this is in a test track, our test track in Sindelfingen. There are some light barriers. There comes our car. And there comes Hans. And Hans is fearless. So first comes the beep, and then comes the reaction. Now, that's not a big deal. I mean, we have shown these demos for many years. But I think the hard part is to make this really reliable and have it perform accurately at every run. Braking just in time. Well, the new thing about this back then was the use of the automatic evasion maneuver. And actually, the system had to choose between automatic evasion and automatic braking, whether it could come to a full standstill or not. So the priority was first braking and otherwise evasion. And the hard part was that the system had only 300 milliseconds to estimate all the velocities and positions to make this distinction. So that was really hard. The way it looks like from the driver, the wheel goes to the left and to the right. Now, if the driver would clench the wheel, then the driver would overrule the system. And I think that that's kind of interesting because this is one instance where the system is actually outperforming an attentive human driver, because the human driver has really difficulties to make this distinction. You know, can I come to a full complete standstill, yes or no? Okay, so that was Hans. And now let's look at the tests with real pedestrians in pre-crash setting. That's what you have been waiting for, hopefully. So let's see. So here we have a volunteer. And here is our fake car. In fact, we have placed all our sensors on this test rig. And so we have a stereo camera, we have radar, we have a far infrared camera. And the clue is, of course, that we have a number of redundant safety cables which are placed over here. And, well, in the last very moment, the test rig decelerates with very high deceleration. And, well, I should mention that those guys who built this device actually were walking here, so I thought that was kind of comforting that they had confidence. If you take a look at the sensor data, it looks quite intense because you can come up to about 3 to 4 meters in front of the pedestrian with like 40-50. So, yeah, it's very interesting data to work on. Okay. Another variation of the testing that we do at Daimler is without using drivers, but using real cars. So this is our version of autonomous driving. And we do that for those cases, for testing those driver assistance functions that need a very high accuracy and that we want to test with a high degree of reproducibility. And so what we have is that we have some devices that we put on, that our colleagues put upon normal cars within one day. And, well, you can also do some maneuvers there which you wouldn't want to do with, well, real drivers. Okay. So I talked about some of the factors that brought us where we're here now. And the question is, so what's next? Okay. Well, you can take that question, what's next, very literally, and wonder, what is the pedestrian going to do within the next second or so? And this is some work that we did, inspired by some human perception studies of Bertolt Ferber at the University of Munich, who had participants watch videos of pedestrians walking towards the curbside, and he asked the test persons what the pedestrians would do. Would they cross or would they stop? And we thought that would be a really neat idea to try to do automatically with the system, and we set forth to outperform the human, right? So let's see how that works. So here is Christoph Keller walking towards the street, and I'd like to ask you, who thinks that Christoph is going to cross the street? Okay, so who thinks that he is going to stop? Okay, what seems to be equally spread. I thought this was kind of easy because the vehicle is standing and we're only looking 5 frames ahead. And in this case, 5 frames comes down to 230 milliseconds, so it's a very short prediction horizon. But in fact, so let's see what happens. Okay, he's thinking about, so here's the system output, and notice the output that will appear over here, so the system thinks that he will cross, and this is the case here. And so here's another case. Okay, I won't ask you again. There's no credit for this one here. Again, we'll see the system in action. So what we do is, in fact, we do a prediction. You can see the prediction of the system by the red cross. The ground truth is shown here by the green circle. And, well, I don't have time to go into details, but the system uses a set of stored trajectories which correspond to many walking and many standing patterns. And what we do is we just match a test trajectory to this database. And the degree of match of a test with a particular training trajectory determines the weight that this training trajectory will have for the path prediction. So it's a probabilistic approach. The technical term is particle filtering. And that's how we do the prediction. And in addition to using 3D position, we also use dense flow features for the matching between the test and training trajectories. Because we believe that by looking at this dense flow image, that we get additional features, additional information about what's going to happen, about the plans of the pedestrians with respect to the 3D single point position. And we're comparing with the human later on, and also with a sophisticated common filter, where the common filter is using multiple motion models. So how well are we doing? How good are we doing? Well, unfortunately, we're not outperforming the human. Not yet. So if you take a look at the accuracy of action classification of determining the right category, walking versus non-walking, then you can see here, this is the accuracy and this is time to event, meaning that where there's 0, that's where the pedestrian is at the curbside, whether he's walking or stopping. So time goes from left to the right, And what you can see here is that the human reaches 80% accuracy already 570 milliseconds before the event, whereas our best system reaches this 180 milliseconds before the event. And the baseline, which was the sophisticated common filter, only reaches that confidence after the event. That's because it's kind of slow to adjust to the probability that the pedestrian might actually continue walking or might stop. So there is some slowness in the filter. And it also shows that, well, comparing this black curve with this red curve, it also shows that there's a benefit of using these dense optical flow features. Now you might say, okay, what's the big deal about 180 milliseconds? I mean, it doesn't sound like a lot, right? But in fact, if you take a look at accident analysis, under some reasonable circumstances, you can show that 180 milliseconds of braking earlier, emergency brake, reduces your chances for a hospital stay by 15%. Okay, so we said that more informative features would help, like dense optical flow. But how about if we would go a step further and also try to recover semantic relevant features like the 3D articulated pose of a pedestrian? So let's look at this video. So here's somebody walking, and we have a full 3D reconstruction. Notice the head movements. So that this really looks good. Unfortunately, well, I cheated, okay? We're not able to do this automatically. Don't believe everything you see. In fact, so there's somebody who's wearing this motion capture suit with a lot of inertial sensors, and that's how we got this. But of course, we would like to do this coming from the sensor data. And I talked about evasion, about situation analysis on a test track, and here's some example of doing that in the urban environment. Here's our car. This is where we're going to be in 2 seconds. Here are some detected pedestrians with their estimated velocities and directions. Here's my former student, and he's on collision course, and you can see that, you know, the car. It's former because he actually graduated. He got his PhD. So you can see here a number of possibilities that we get once we have detected a collision. But this is a bit exaggerated because we have an artificially large prediction horizon of 2 seconds just to see something. If I just redo it. And then you can also see the last possible moment where the car could have braked, okay? And you can see here only the pedestrians, but we have similar, so this is the braking here. The last possible moment would be here to start braking. But we also have the analysis where we can deal with arbitrary objects that we segment together using a technique we call dynamic stigsels for object segmentation, and we can get cars and other moving objects. Okay, so I'm nearing towards the end. I talked the whole time about pedestrian sensing, and some of you might think, well, what about other things, right? We still have to do some sensing, but we should ought to pay more attention to what the driver is doing. Okay, so we have some colleagues at Daimler that are working on driver intention estimation based on the head pose, based on the use of various instruments, and also based on the trajectory of the vehicle. And then another active area of research is the communication area, and some colleagues are working on placing some active tags on pedestrians, and so there is some communication with a car which comes, and this is especially, the communication approaches are especially useful in cases of visibility obstructions, in case of occlusion. And similarly, you can think of a car communicating with the infrastructure, where at some intersections there are various stationary cameras that maybe have a much better view of the situation rather than an oncoming car, and it would communicate the information to the car. Okay, so now I've come to my final slide. This has been a great decade for computer vision in intelligent vehicles, and this has been also a great decade for pedestrian sensing, and we have made some very remarkable progress. The problem hasn't been solved yet. I mean, there's still some challenges for difficult sensing conditions, especially for occlusions, partial occlusions. And we ought to get better at figuring out, what are the features that are indicative of pedestrian future behavior. But other than that, the next frontier is the situation analysis, understanding the traffic scene in the urban environment, and also putting together information that we get from sensing the environment, communication with the environment, and also using prior knowledge that we might have from digital maps and taking it into account the driver intent. And I think when we have all these pieces together, it won't take too long that the systems that we get will outperform the human drivers, also those that are attentive. And I started the presentation on pedestrians with the accident numbers. And I also would like to end with the accident numbers, because in-depth accident analysis shows that the current generation of driver assistance, which does longitudinal control, which does braking, that this can reduce the traffic accidents. So we have a 20% decrease of, in a sense, of collision avoidance. And we have further 25% collision mitigation with respect to the baseline of having no driver assistance. And we are very excited about the prospect that now, by having specific systems that extend the coverage to pedestrians and bicyclists, that we can get a further reduction of these accident numbers. And so that brings me to the final and only formula for today, which is that better algorithms and market-ready hardware, more data, and extensive testing means more lives saved. Thank you very much, and thanks to the people who contributed.
Thanks a lot, Dariu, for your excellent presentation. Now it's time for your questions.
Yes, we have here. Go ahead.
Thank you. It was a very impressive presentation. I have two questions or comments, if you like. The first thing is, of course, the typical, we have 95% or so of hit rate. But for the remainder 5%, besides the statistics, you get some annoyance from the noise, the warning signal that comes, and you find out by experience that there was nothing. It was just a failure of the system. After some while, you get nervous and you rather disregard any kind of warning signal. That's one typical reaction of a real driver. So therefore, the other avenue I had in mind is, do you have any way for a kind of confidence guarantee that there is for somebody that may be wrong, but at least, if you had a confidence in certain cases, whereas in other cases you're not sure. A typical driver, a safe driver, would just brake anyway.
Well, so to come to your first question, it's really important that these systems that we introduce do not work worse than not having any systems. So that means, first of all, that on this ROC curve, we are very interested in having 0 false alarms at the overall system level. So we would rather not detect all pedestrians, but make sure that there's no false alarms. And to the other aspect of robustness, there are several modules which work together or in a cascade to make sure that there's no kind of hallucination or braking on some hallucinated targets. So I mentioned already that we have things like obstacle detection, things like classification, but then there is also radar, and there is also some integration over time, so that typical hallucinated objects appear very briefly in a sensor and then disappear. So there are a couple of things that we can do to make sure that at the end of the pipeline, no false alarm is performed, especially not in the case where we're going to do emergency operation.
The second comment had to do with the different problem, or with a different way to go about things. Say, you want to make sure as a driver, as long as there's no sound, no alarm sounding, there's no problem. That's completely different from your approach right now. But it may add something to a solution that works in practice with not too much of investment.
Yes, your point is well taken, that you will have to have systems that if they warn, they don't do that too often, because otherwise you're not paying attention to the system anymore. That's right.
Do you think we need more cameras, especially to the both lateral side? Because in Japan, many pedestrian or bicycle involved accidents happen when the bicycle and the car comes in the same direction, and one of them plan to make a turning behavior. And I think this kind of system should help human driver to see where it is difficult for them. How about think about that?
Yeah, you're totally right. Although I must say that I'm already happy that we would get 1 or 2 cameras in the vehicle and having a field of view of about 50%. And you have to realize that we're competing with other applications, so we're going to put a lot of applications into using the same sensor setup. So there is a kind of a trade-off on the number of pixels you want to spend on detecting objects far away or in the lateral domain. But yeah, you're absolutely correct. If we get a better lateral view, then we might do even better. Yeah, that's correct. Schedule.
Yeah, we keep the schedule. Also, we can further discuss during the. Oh, okay.
Following up on your comment on lateral field of view, if you look into GIDA's statistics, if I recall correctly, about 25% of the pedestrians actually strike the side of the vehicle. So what should we do then? Basically, it's the pedestrian that runs into the vehicle. Most of those are with very low speed, but or do we really require to handle that or in the future? That would mean that we need 180-degree plus field of view.
Well, we'll definitely have to increase the field of view, but you have to realize that we'll never get the solution for the pedestrian that just jumps 2 meters in front of the car. I mean, it's even physically, okay, we might do something with airbags, but those cases, we won't be able to do much by braking or evasion if it really happens in the last moment. But other than that, I totally agree. We will get better if we increase the field of view, yeah. Okay.
Thanks again, Dariu, for your presentation.
Thank you.